In 2019, 19.7% of the U.S. energy supply was provided by nuclear power. This is according to the U.S. Energy Information Administration's page titled What is U.S. Energy Generation by Energy Source, published February 27, 2020. In this speech, I will inform the class of Com 110 about nuclear energy. I will discuss some brief history about nuclear energy, nuclear fission, and nuclear fusion. Now I'll move on to my main points. The first one I will talk about is nuclear energy's history. And nuclear energy really begins around 1895 with the discovery of the X-ray when Wilhelm Rothenberg was messing with exposure of cathode rays. And in 1896, they found out that the same kind of exposure was coming from uranium pellets, and two scientists, Marie Curie and her husband Pierre, would observe this phenomenon and would later coin the term radioactivity and would discover polonium and radium. In 1920, the neutron would be discovered. This was important for nuclear theory because it was important to understanding the nucleus of an atom. And in 1941, we would actually achieve the first man-made fusion. It was in a small scale and it didn't last long, but it was progress nonetheless. During this time, a lot of nuclear theory was aimed toward the creation of the atomic bomb, and it wouldn't be until 1951 that we would have an experimental reactor. This reactor, titled EBR-1, was a liquid metal cooled reactor, and it was the first one to generate electricity. And the ideas they learned from this would be used in 1954 when the first nuclear submarine was built, in which its propulsion was entirely made from the electricity produced from a nuclear reactor. It wouldn't be until 1957 that we would have the first commercial reactor, though. After this, though, nuclear energy would be heralded as the future when it came to energy. It got a lot of support, even coining the period of time in which it was the main focus, the atomic age. It got so much support so that in 1974, 75% of France's power was coming from nuclear power plants. And after this, nuclear energy would stagnate because people were getting a lot more interested in the drawbacks of such a thing, mainly nuclear waste and even more scary, nuclear meltdowns, such as Three Mile Island incident in 1974, Chernobyl in 1986, and even more recently in 2011, Fukushima. This would basically put nuclear reactors on a back burner because the public was scared of it. But that is some of the brief history of nuclear power. If you want more information, you can check out my source, whatisnuclear.com. It's page history of nuclear energy. I last accessed it October 22nd. My next point is nuclear fission. Nuclear fission is the process by which they bombard a radioactive element with a proton, and it deforms the element and causes it to split into two lighter elements and produce radiation, thermal energy, and roughly three protons, as a byproduct. These protons would then go and hit other uranium atoms and cause the same thing to happen to them, resulting in a chain reaction. If you want to learn a lot more about the intricacies of a nuclear fission reaction, I recommend checking out my source Steinberg's nuclear fission page on Britannica that was published July 29th, 1999. But typically in a reactor, the element they use is uranium, and they process these uranium pellets and they put them into tubes that they group up into two groups of 200. These fuel rods then turn into fuel assemblies when there's 200 of them there. And then these fuel assemblies would be put like there would be hundreds of them in these reactors, depending on how powerful you wanted the reactor to be. And in these reactors, you would have water acting as a coolant and a mediator to slow down the reactions, because a chain reaction unhinged leads to a nuclear meltdown. And in the US, there's two designs mainly in use. They're both light water reactors. They're named a pressure water reactor and a boiled water reactor. They operate about the same principle, but slightly different. A pressure water reactor has a main reactor core in which it is filled with water, and in the middle of that water, there will be the fuel rods. These fuel rods would be constantly getting hit by protons from each other due to the chain reaction, and the thermal energy they would be off-putting would be heating the water around it, and as heat rises, the water would rise to the top of the reactor core, and then it would be funneled off into a tube that would be located in a heat exchanger. This heat exchanger is filled with water. That water boils, produces steam. That steam gets pumped into a turbine, which spins and then produces energy. And as the steam cools down, it turns into water and goes back into the heat exchanger. And as the water in the heat exchanger cools down, it goes back into the reactor core. A boiled water reactor, though, takes that concept and basically gets rid of the heat exchanger. It takes the reactor core, fills it about halfway or some other percentage, and has it boil the water directly in there. And as the water boils, it heads to the top of the reactor core and then is funneled directly to a turbine. According to um, the Office of Nuclear Energy's page titled Nuclear 101, How Does a Nuclear Reactor Work? That was published May 19th, 2020. About 70 something percent of the US reactors are pressure water reactors. That is the basis of nuclear fission and some of the designs utilizing it. For my last point, I will talk about nuclear fusion. Nuclear fusion is a very tough challenge because the only place we can actually observe it happening is the sun, where there is a lot of pressure and a lot of heat. And in a nuclear fusion reaction, the pressure and heat will get the atoms so excited that when they run into each other, instead of splitting apart, they fuse together into a heavier element. On Earth, we cannot replicate the same pressures because we just do not have the technology to do so. So we heat it up to basically hotter than the sun. And the two isotopes of hydrogen that we use for this reaction are deuterium and tritium. Deuterium is a actually very common element that you can find in water, but tritium is very rare and scarce in nature and is slightly radioactive with a half-life of around 12 years. If you'd like to know a little bit more about nuclear fusion's uh, challenges when it comes to engineering, you can check out my source, NAE Grand Challenges for Engineering's page, Provide Energy from Fusion, that I last accessed October 22nd. But the nuclear fusion has basically three main types of realizing it: magnetic confinement fusion, inertial confinement fusion, and magnetic target fusion. In magnetic containment fusion, the reactor basically uses strong electromagnetics combined with plasma that is filled with deuterium and tritium to utilize the basic interaction that plasma has with electromagnets to confine the reaction and basically allow them to heat it up and stable. It's meant to keep the reaction occurring because since it's not a chain reaction, it requires constant heating. Since it won't heat itself. But inertial confinement fusion actually takes a pellet of deuterium tritium and hits it with an ion beam, and this heats the outside of the pellet. But during this, the pellet actually starts imploding on itself and compressing, and that compression actually causes it to heat up to where fusion can actually occur. Magnetic target fusion, though, basically takes the compression idea with the ion laser and combines it with the electromagnetics and plasma. And the most common one used is magnetic containment fusion with tokamak reactors and stellarators. Tokamaks are basically a giant torus. I recommend checking out ITER, ITER. It is a multinational project. But if you want to learn more about nuclear fusion itself, I recommend checking out my source, World Nuclear Association's page titled Nuclear Fusion Power, that was published in July 2020. But that is nuclear fusion and some of the ideas behind it. I have talked about some of the brief history of nuclear energy and nuclear fission and nuclear fusion. Um, According to World Nuclear Association, nuclear power in the world today, published in August 2020, roughly around 10.1% of the world's total energy was actually produced by nuclear reactors. It's still in use today and it is a viable use. I'd like to thank you for taking the time to listen to my speech.